Saturn, the jewel of our solar system, glitters with secrets that even the most advanced telescopes can't fully unravel. Its breathtaking rings, stretching wider than the distance between Earth and the Moon, hide more than just icy debris. They guard puzzles that baffle scientists to this day. But the mysteries don't stop there. From ancient myths that revered Saturn as a god to modern discoveries that defy explanation, this planet has always been a cosmic enigma. What if I told you some of its strangest phenomena still have no answers? Today, we're diving into 25 of Saturn's most perplexing mysteries, the kind that make astronomers scratch their heads and wonder if we've only begun to uncover the truth. Ready to question everything you thought you knew about this ringed giant? Let's begin. One of the most striking mysteries of Saturn isn't found in its dazzling rings, but at its North Pole. Picture this, a colossal, near-perfect hexagon, wider than Earth itself, churning in the planet's atmosphere. This isn't some trick of the light or a camera glitch. It's a real, persistent storm with 6 razor-sharp sides, spinning like a cosmic top for decades. When Voyager first spotted it in the 1980s, scientists thought it might be a temporary anomaly. But Cassini's later observations confirmed this hexagonal monster isn't going anywhere. What makes it even stranger, Jupiter's great red spot is chaotic, a swirling mess of turbulent winds. But Saturn's hexagon is eerily precise, a geometric oddity in a place where nature usually avoids straight lines. Some researchers think deep-rooted jet streams create standing waves, locking the storm into this shape. Others speculate hidden forces beneath Saturn's clouds might be sculpting it like an invisible hand. Yet, no theory fully explains why it stays so stable while the planet's turbulent atmosphere rages around it. Here's the kicker: we've seen hexagonal patterns form in controlled lab experiments with spinning fluids, but nothing on this scale, nothing so persistent. So is this a clue to Saturn's hidden mechanics, or just another cosmic curveball? Either way, it reminds us that even in our own solar system, some puzzles refuse to play by the rules. The hexagon isn't just a flat, two-dimensional shape, it's a towering wall of clouds stretching hundreds of kilometers high, with winds howling at speeds over 300 miles per hour. At its heart lies another marvel, a massive hurricane-like vortex swirling with the same eerie precision as the hexagon itself. Think of it like the eye of a storm, but one that's been locked in place for decades, unshaken by the chaos around it. And here's something even more puzzling. This phenomenon only appears at Saturn's North Pole. The South Pole, nothing like it, just ordinary turbulent storms. Why the asymmetry? Some scientists believe it's tied to Saturn's extreme seasons. Each season lasts roughly 7 Earth years, and as the planet tilts, sunlight shifts dramatically across its poles. The hexagon might be a product of this slow dance between light and darkness, with atmospheric currents reacting in ways we don't yet fully grasp. Then there's the question of depth. Unlike Earth storms, which are relatively shallow, Saturn's hexagon could extend thousands of kilometers below the cloud tops, anchored by forces buried deep within the planet. Could hidden layers of gas or even Saturn's internal heat be shaping this storm from below? Or is it something more exotic, like interactions with the planet's powerful magnetic field? Every time we think we're close to an answer, Saturn throws another curveball. The hexagon defies our expectations, proving that even in our own cosmic backyard, nature still has a few tricks up its sleeve. While Saturn's hexagon dazzles with its geometric perfection, the rings surrounding the planet hold their own bizarre secrets, features so strange they look almost supernatural. Picture dark, ghostly streaks stretching like bicycle spokes across the rings, appearing and vanishing without warning. These eerie formations, simply called spokes, glide over the icy particles as if something or someone is drawing them there. But what's really behind these fleeting cosmic brushstrokes? First spotted by Voyager in the 1980s, the spokes baffled scientists for decades. Unlike the rest of Saturn's rings, which follow predictable orbits, these radial streaks seem to dance to their own rhythm. They're not made of ice like the surrounding ring material. Instead, they're likely clouds of tiny charged particles hovering just above the ring plane. And here's the twist: they show up more often during Saturn's equinoxes, when sunlight strikes the ring's edge on. So what's triggering them? One leading theory points to electrostatic forces. As the rings pass through Saturn's shadow, the sudden temperature drop might zap tiny ice grains, sending them floating above the surface like celestial dust devils. Others suggest micrometeoroid impacts could be kicking up debris, creating temporary ripples in the ring's delicate balance. There's even speculation that Saturn's own magnetic field plays a role, guiding these particles into their strange, transient path. But the biggest mystery isn't just how they form, it's why they vanish. Some spokes linger for hours, others disappear in minutes, leaving no trace behind. Are they dissolving back into the rings or being swept away by unseen forces? Even Cassini, which studied Saturn for over a decade, couldn't crack the code. The spokes remind us that Saturn's rings aren't just a static backdrop, they're a dynamic, ever-changing stage, where particles the size of dust grains can create enigmas that rival the planet's grandest storms. And just when we think we've got them figured out, they slip through our fingers like cosmic whispers. Saturn's magnificent rings, the very feature that makes it instantly recognizable, are vanishing before our eyes. Scientists call it ring rain, a slow but relentless downpour of icy particles pulled by Saturn's gravity, draining the rings like sand through an hourglass. The Cassini spacecraft made the chilling discovery during its final orbits. Every second, enough material to fill an Olympic-sized pool cascades into the planet's atmosphere. At this rate, projections suggest the rings could be gone in just 100 million years, a blink of an eye in cosmic time. But this raises an even deeper mystery. If the rings are disappearing so quickly, why do they still exist at all? Saturn itself is over 4 billion years old, ancient compared to its rings, which some studies suggest might be a mere 100 million years young. That's like a grandparent wearing a brand new piece of jewelry. How did such a youthful ring system form around an aging planet? One theory points to a catastrophic event, perhaps a moon torn apart by Saturn's gravity or a comet shattered in a violent collision. The debris could have spread into the stunning disks we see today. Yet, other researchers argue the rings might be older but constantly replenished by hidden icy moons feeding them fresh material. The truth is, we've caught Saturn's rings in a fleeting moment of their existence, glorious now but destined to fade. What's certain is we're witnessing a cosmic balancing act. As gravity drags the rings downward, other forces like micrometeoroid impacts blast particles outward, creating a fragile equilibrium. The Cassini mission gave us front-row seats to this slow-motion disappearance, a reminder that even the most iconic celestial wonders are temporary. So the next time you gaze at Saturn's rings, remember, you're seeing a masterpiece in its final act. Among Saturn's many moons, one stands out as a world of astonishing contradictions: Enceladus. At first glance, it's just a tiny, icy sphere, barely 300 miles wide. But look closer, and you'll find it's a cosmic fire hose, blasting towering plumes of water vapor and ice high into space from its south pole. These aren't just occasional sputters, they're continuous, violent eruptions, shooting material hundreds of miles above the surface, enough to feed one of Saturn's outer rings. What makes these geysers so extraordinary? Beneath Enceladus' frozen crust lies a vast, global ocean of liquid water, kept warm by tidal forces as Saturn's gravity stretches and squeezes the moon. That same energy cracks the icy shell, creating deep fractures called tiger stripes, where water erupts like steam from a pressure cooker. But here's the real kicker. Cassini flew through these plumes and detected organic compounds, the chemical building blocks of life. Not just simple molecules, but complex ones like methane and propane, hinting at chemical reactions that could, under the right conditions, support microbial life. Yet Enceladus isn't the only icy moon in the solar system. Europa, orbiting Jupiter, also hides a subsurface ocean, but it doesn't spew its secrets so brazenly into space. So why is Enceladus so different? Scientists suspect its ocean might be in direct contact with a rocky seafloor, where hydrothermal vents could brew a rich soup of minerals and energy. It's a scenario eerily similar to Earth's deep-sea vents, where life thrives without sunlight. Could the same be happening under Enceladus ice? The more we learn, the stranger it gets. Some of these geysers flicker like cosmic strobe lights, pulsing in sync with Saturn's gravity. Others leave behind a faint, mysterious sodium signature, suggesting hidden chambers of briny water. Every answer leads to new questions. If life exists there, it wouldn't be green or scaly, it'd be tiny, tenacious, and utterly alien, surviving in darkness under crushing pressure. Until we send another mission to taste those plumes directly, Enceladus will keep its secrets locked beneath the ice, a tiny moon with cosmic implications. Beneath Enceladus' frozen surface lies an engine of incredible power, one that turns this small moon into a cosmic fountain. The question is, what keeps this system running? Two prime suspects emerge: tidal heating and radioactive decay. Both could provide the energy needed to maintain a liquid ocean under miles of ice, but which one plays the bigger role? Tidal heating seems the most likely culprit. As Enceladus orbits Saturn, the planet's immense gravity stretches and compresses the moon like a rubber ball, generating friction deep inside. This constant flexing creates heat, melting the ice below the surface and maintaining the vast underground ocean. The tiger stripe fractures at the South Pole act as release valves, thin spots in the icy shell where pressure forces water vapor and ice crystals to burst free. It's a delicate balance: too much heat and the ocean might boil away, too little and the geysers would freeze solid. But radioactive decay can't be ruled out. Heavy elements like uranium and thorium, left over from the moon's formation, could still be breaking down deep within its rocky core, releasing steady warmth over billions of years. Some scientists argue it's a combination of both: tidal forces doing the heavy lifting while radioactive elements provide a slow, steady boost. What's truly baffling is why Enceladus is so much more active than similar moons. Europa, for example, also has an underground ocean and experiences tidal heating, yet its surface remains mostly quiet. The answer might lie in Enceladus' peculiar orbit. It shares a gravitational tug-of-war with another moon, Dione, which keeps its interior constantly churning. This extra squeeze could be just enough to turn Enceladus into a celestial geyser, while other moons remain dormant. The tiger stripes add another layer to the mystery. These long, parallel cracks aren't random, they're direct pipelines from the ocean to space, shaped by the moon's internal stresses. Some even glow faintly with excess heat, like wounds that never heal. If we could dive beneath them, we might find hydrothermal vents churning out minerals, or even strange chemical reactions that hint at something far more extraordinary. Enceladus doesn't just hide its secrets, it sprays them into the void, daring us to look closer. Measuring time on Earth is straightforward: one rotation equals 1 day. But Saturn laughs in the face of such simplicity. Here, the very definition of a day becomes a cosmic riddle, with scientists still debating its exact length decades after our first close-up observations. The trouble: Saturn refuses to sit still long enough for us to clock it properly. Unlike rocky planets with solid surfaces, Saturn is a swirling ball of gas with no fixed landmarks to track. Early estimates relied on watching cloud patterns, suggesting a day around 10 hours and 39 minutes. Then came the magnetic field data, which threw everything into chaos. When Cassini measured Saturn's magnetic pulses, An internal heartbeat of sorts, it pointed to a day almost 6 minutes longer than the cloud-based calculations. 6 minutes might not sound like much, but for planetary scientists, it's a glaring discrepancy that shakes our understanding of how gas giants behave. So why the mismatch? Some researchers think deep winds might be skewing the magnetic field, dragging it out of sync with the planet's true rotation. Others propose that Saturn's core isn't a neat, compact sphere but a diffuse, layered structure that rotates unevenly like a spinning top wobbling on a table. There's even a wild card theory. Electrically conductive helium rain sinking through the interior could be altering the magnetic signals, tricking our instruments. The irony: Jupiter, another gas giant, has a well-defined rotation rate, but Saturn's deeper atmosphere and complex internal dynamics make it a tougher nut to crack. Every new observation adds another twist. Recent studies using ring vibrations as a sort of planetary seismograph suggest yet another possible day length, further muddying the waters. One thing's certain: until we land a probe deep in Saturn's churning atmosphere or develop technology to peer through its layers, this celestial clock will keep us guessing. It's a reminder that even the most fundamental facts about our solar system can remain slippery, especially when dealing with a planet that plays by its own rules. Saturn's moon, Iapetus, is a cosmic paradox, a world split straight down the middle, like two mismatched puzzle pieces forced together. One hemisphere gleams as bright as fresh snow, reflecting sunlight with dazzling intensity. The other, a charcoal dark abyss, so devoid of light it might as well be carved from the night sky itself. This isn't subtle shading, it's the solar system's most extreme case of planetary split personality disorder. The contrast is so stark that when astronomer Giovanni Cassini first spotted Iapetus in the 17th century, he noted it seemed to vanish when one side faced Earth. Centuries later, we now know why. That dark region absorbs nearly all sunlight, while its twin reflects almost all of it. But what could create such a dramatic divide? One leading theory points to thermal segregation, a slow, relentless process where sunlight subtly shifts material across the moon's surface. Here's how it might work. Dark areas absorb more heat, causing nearby ice to vaporize and migrate to colder, brighter regions. Over eons, this runaway effect could amplify the contrast, like a cosmic feedback loop, painting one side black while bleaching the other white. Yet there's a wild card: that dark material might not even belong to Iapetus. Some scientists argue its debris blasted off Phoebe, a distant, dark-colored moon, and later swept up by Iapetus' leading face. Imagine driving through a rainstorm. Your windshield catches more droplets than your rear window. Similarly, as Iapetus plows through its orbit, one side could accumulate more of this cosmic soot. But here's the catch: neither theory fully explains the razor-sharp boundary between light and dark. There's no gradual gradient, just an abrupt line, as if drawn by some celestial artist. Even more puzzling, the darkest patches align perfectly with impact basins, suggesting the moon's own geology might play a role we don't yet grasp. Thermal segregation, foreign debris, hidden processes beneath the surface. Iapetus keeps its secrets locked behind that eerie two-toned mask, challenging us to look deeper. Perhaps the real mystery isn't just how this moon became so divided, but why no other world in our solar system wears its contradictions so boldly. Until we land a probe on that stark border between light and shadow, Iapetus will remain a silent enigma, a yin-yang symbol etched into the cosmos. Saturn's moons, Janus and Epimetheus, perform a celestial maneuver so bizarre, it defies intuition, an orbital waltz where two worlds trade places without ever touching. Imagine two race cars circling the same track, constantly adjusting speed to avoid collision, yet never quite passing each other. That's essentially what happens here, but on a cosmic scale. These lumpy, potato-shaped moons orbit so close together, separated by just 30 miles, that their gravitational tug of war forces them into a rhythmic swap every 4 years. One moon slows down, drifting outward, while the other speeds up, slipping inward. Then, like perfect dance partners, they exchange positions without a hint of chaos. This isn't just a quirky coincidence, it's a gravitational feedback loop so precise it feels almost engineered. Normally, objects sharing an orbit either collide or fling each other into space. Yet Janus and Epimetheus have maintained this delicate balance for millennia, locked in what scientists call a horseshoe orbit. Their dance suggests they might have started as a single moon, shattered by an ancient impact, leaving fragments trapped in this elegant equilibrium. But here's what really stumps researchers: their shared orbit shouldn't be stable. Calculations show tiny perturbations. A passing comet's gravity or even the pull of Saturn's rings should have sent them crashing together long ago. The fact they haven't implies something else is at work, perhaps a subtle interplay with Saturn's other moons or hidden resonances in the planet's gravity field. Their surfaces tell another story. Janus, the larger of the two, bears deep grooves that might trace back to this endless orbital shuffle stress fractures from perpetual gravitational stretching. Epimetheus, meanwhile, appears oddly smooth, as if its surface constantly resets itself during each swap. Are these moons actively shaping each other's geology, or is their dance merely a surface-level symptom of deeper mysteries? For now, this gravitational pas-de-deux remains one of Saturn's most exquisite puzzles, a reminder that even in the cold void of space, celestial bodies can move with unexpected grace. Every 4 years, the clock resets and the dance begins anew, challenging our assumptions about how moons form, evolve, and survive in the chaos of the cosmos. Turn your attention to Titan, Saturn's largest moon, a world where rivers carve valleys into ice instead of rock, and rain falls not as water but as liquid methane. Yet even among its alien landscapes, one feature stands out as truly otherworldly: a colossal polar vortex swirling over the South Pole like a monstrous hurricane trapped in time. This isn't just another storm, it's a churning maelstrom of toxic chemicals, towering hundreds of kilometers high, with temperatures cold enough to freeze Earth's atmosphere solid. What makes this vortex so bizarre? Unlike Earth's polar vortices, which weaken and shift with the seasons, Titan's version clings stubbornly to its perch, resisting change even as sunlight fades during the moon's long winter. Cassini's infrared eyes revealed why. This vortex isn't spinning with water vapor or ordinary clouds, it's packed with hydrogen cyanide and other deadly organic compounds, freezing out of the frigid atmosphere like poisonous snow. Here's the real puzzle. On Earth, polar vortices form because of temperature contrasts between the pole and equator. Titan's dense, hazy atmosphere should spread heat more evenly, making such extreme vortices unlikely. Yet there it is, a relentless whirlpool of gases defying expectations. Some scientists think hidden atmospheric waves similar to Earth's jet streams but laced with hydrocarbons might be funneling energy into the storm, sustaining it like an engine running on alien fuel. Then there's the seasonal twist. When Cassini arrived in 2004, Titan's South Pole was basked in summer sun. But as winter approached, the vortex didn't dissipate, it intensified, growing colder and denser. This suggests the vortex isn't just a weather pattern. It's a dynamic trap, a place where Titan's atmosphere dumps its most complex molecules, creating a swirling laboratory for chemistry we can barely comprehend. What could these reactions be brewing? The same compounds found there are precursors to life's building blocks, raising tantalizing questions about what might linger in Titan's hidden layers. While Earth's vortices come and go, Titan's endures, a frozen tempest guarding secrets at the edge of our understanding. One thing's certain, this isn't just a storm. It's a window into how alien atmospheres sculpt worlds beyond our own. Titan's methane lakes should hold more than just methane, they should be swimming with ethane. This thicker, heavier hydrocarbon is a natural byproduct of Titan's atmospheric reactions, where sunlight breaks methane apart and reassembles it into complex chains. Yet when Cassini mapped Titan's surface, it found far less ethane than expected. Where did it all go? One possibility lies beneath the surface. Just as Earth hides vast aquifers of groundwater, Titan might have underground reservoirs brimming with liquid ethane, seeping through porous ice like syrup through a sponge. These hidden pockets could act as chemical storage units, keeping ethane out of sight but not out of the equation. Some models suggest cryovolcanoes, cold, slow-moving ice volcanoes, might even release bursts of trapped ethane when they erupt, briefly spiking surface concentrations before the liquid drains away again. But there's another twist. Titan's chemistry might be far more dynamic than we imagined. On Earth, bacteria break down hydrocarbons over time. While we're not suggesting life on Titan yet, unknown chemical processes could be converting ethane into even heavier molecules like benzene or acetylene, leaving behind barely a trace. Laboratory experiments show that under Titan's extreme cold, ethane can form slushy clathrates, ice-like cages that trap molecules, effectively removing them from the liquid cycle. The mystery deepens when you consider Titan's age. Over billions of years, atmospheric reactions should have produced enough ethane to coat the entire moon several meters thick. Instead, we find mere puddles. Could seasonal changes be at work? Titan's long, slow seasons, each lasting roughly 7 Earth years, might periodically bury ethane under layers of organic haze or freeze it into vast, undiscovered underground glaciers. Every missing drop of ethane is a clue pointing to processes we've yet to crack. Whether it's hiding beneath the ice, transforming into something stranger, or being recycled by Titan's alien weather, one thing's clear: this moon's chemistry is playing by rules we're only beginning to decode. Saturn's moon Hyperion looks like it's been through a cosmic shredder, a jagged, pockmarked world with a surface so porous it could float in a bathtub if one existed large enough. Imagine a giant sponge, but one blasted by countless meteorites, leaving behind a honeycomb of craters within craters. This isn't just another rocky satellite. It's one of the most bizarrely textured objects in the solar system, defying every expectation of how a moon should behave. Hyperion's low density tells part of the story. It's mostly empty space, with gaps between loosely packed ice and rock making up nearly half its volume. Most moons compact over time, but Hyperion seems to have avoided this fate entirely. Some scientists think it might be a remnant of a larger body shattered by an ancient collision, its fragments reassembling into this fragile, open structure. The craters support this. Many are unusually deep, as if impacts punched straight through its brittle shell without resistance. Yet here's the real puzzle: Hyperion shouldn't exist in its current state. Even gentle tidal forces from Saturn should have pulled it apart or compressed it into something denser. Instead, it tumbles chaotically as it orbits, rotating unpredictably like a poorly thrown football. This erratic motion might be its saving grace without a stable orientation. It never faces Saturn long enough for gravity to reshape it. Then there's the strangest detail of all. Its spongy surface seems to preserve impacts rather than erasing them. Most celestial bodies smooth out over time as debris fills their craters, but Hyperion's porous structure might absorb collisions like a celestial shock absorber, leaving each scar eerily intact. Even cosmic dust doesn't cling to it well. Images show dark material settling only at the very bottoms of craters, as if the rest of the moon repels it. The more we study Hyperion, the clearer it becomes this isn't just a moon. It's a frozen fossil of chaos, a testament to the violence of the early solar system. Why it remains so fragile, so untouched by the forces that sculpt other worlds, is a mystery written in craters and shadow. Until we land a probe on its fractured surface, Hyperion will keep its secrets locked in those countless voids, a cosmic sponge drifting through the void. Saturn's moon Mimas might look unremarkable at first glance, just another cratered ice ball in the void. But when scientists pointed infrared sensors at it, they found something utterly bizarre: a heat map shaped exactly like Pac-Man, the iconic video game character. That's right, this frozen world has a thermal signature that looks like it's straight out of an arcade. The mouth of this cosmic Pac-Man lines up perfectly with Herschel crater, a massive impact feature so large it nearly shattered the moon. But the rest, temperatures drop sharply along those razor-straight edges, creating a geometric heat pattern that defies natural explanations. Normally, heat distributes evenly on airless worlds, fading gradually from warm to cold. Mimas, though, flips the script. Its surface isn't just unevenly heated, it's divided with eerie precision, as if someone traced the outline with celestial chalk. So what's causing this arcade-worthy anomaly? One theory suggests that Herschel crater's impact altered the moon's surface structure, creating a maze of compacted ice that retains heat differently than the untouched regions. Imagine dropping a heavy rock into fresh snow. The packed snow underneath stays colder longer, while the fluffy stuff around it warms faster in sunlight. That could explain the stark thermal divide, but there's a wilder possibility. Mimas might be hiding a subsurface ocean. For years, scientists dismissed the idea this moon is tiny, with no visible geysers or cracks like Enceladus. Yet recent models show that if an ocean exists, tidal heating from Saturn could create just enough warmth to generate this odd heat pattern. The Pac-Man shape might then be thermal walls where cold, rigid ice sits atop warmer, slushy layers beneath. It's a cosmic tug of war between two explanations, one rooted in surface scars, the other in hidden oceans. What's certain is that Mimas, the solar system's smallest round moon, shouldn't be this strange. Yet there it is, glowing in infrared like a relic from gaming history, daring us to press start and uncover its secrets. Saturn's rings aren't just smooth sheets of ice, they're dynamic, ever-changing landscapes where tiny hidden moons leave their mark in the most unusual way. Meet the propeller moonlets, miniature worlds no bigger than a city block, yet powerful enough to carve whimsical, S-shaped gaps in the rings as they orbit. These aren't your typical moons with craters and valleys, they're more like cosmic bulldozers, pushing ring particles aside as they glide through the debris. Cassini first spotted these propeller-shaped disturbances in the mid-2000s, revealing a population of moonlets too small to clear full-fledged gaps like Pan or Daphne's, but still massive enough to leave a gravitational signature. Each one creates a two-winged pattern in its wake, resembling the twist of an airplane propeller frozen in ice. Scientists even nicknamed them after famous aviators Blériot, Earhart, Santos Dumont, honoring their elegant airborne shapes. What makes these moonlets so puzzling? For starters, they shouldn't survive long in such a chaotic environment. Saturn's rings are a demolition derby of particles, where collisions should grind small objects to dust within millennia. Yet here they are, persisting as if defying the odds. Some researchers think they might be armored with dense cores, barely holding themselves together under constant bombardment. Others suggest they're temporary aggregations, clumps of rubble that form and dissolve like sandcastles in a tidal zone. Their existence also hints at a hidden chapter in moon formation. In most models, moons grow by steadily accumulating material in open space. But propeller moonlets seem to have formed within the rings themselves, emerging from the very material they now push aside. If true, they could be a snapshot of how larger moons like Enceladus or Tethys began tiny seeds in a disk of debris, slowly gathering mass over eons. Yet every answer raises new questions. Why do some propellers appear freshly carved while others look smudged and faint? Are they actively growing or slowly disintegrating? And could there be thousands more, too small for us to spot? These miniature architects remind us that even Saturn's grandest features owe their existence to the smallest players, worlds so tiny they're almost invisible, yet bold enough to leave their signature on the cosmos. Hidden within Saturn's dazzling rings lies a chemical surprise. An invisible layer of oxygen-rich molecules buzzing with electric energy. When Cassini skimmed the rings, its instruments picked up something straight out of Earth's playbook. compounds eerily similar to ozone, the same shield that protects our planet from harsh ultraviolet rays. But here's the twist: Saturn's version isn't guarding a surface or an atmosphere. It's crackling to life in the most unlikely place imaginable, the frigid, airless gaps between icy ring particles. So how does oxygen even form in such a hostile environment? Blame radiation. As Saturn's magnetic field bombards the rings with high-energy particles, they blast apart water molecules locked in the ice, freeing oxygen atoms that then recombine into new, exotic compounds. It's a process shockingly similar to what happens in Earth's upper atmosphere, where solar radiation splits oxygen to create our protective ozone layer. The difference: Earth's ozone blankets a planet, Saturn's dances on razor-thin ice fragments, a ghostly chemical whisper in the void. But the real stunner isn't just the presence of these molecules, it's their behavior. Unlike Earth's stable ozone layer, Saturn's ring chemistry is dynamic and fleeting. Some molecules cling to ice grains like static-charged dust, others zip through the gaps pulled by the planet's magnetic tides. This creates pockets of temporary ring ozone, flickering in and out of existence like neon signs in a cosmic storm. What's the big takeaway? For decades, we assumed complex chemistry needed an atmosphere or an ocean. Saturn's rings prove otherwise. They're not just icy relics, but active laboratories where radiation rewrites the rules. If simple ice and energy can brew oxygen in deep space, what other chemical miracles might be hiding in plain sight? Every flicker of ring ozone is a clue, forcing us to rethink where and how the building blocks of life might emerge. Saturn's moon Tethys should be a blank canvas, a serene, icy sphere peppered with craters. But look closer, and you'll find something that shatters that illusion: eerie, blood-red streaks slicing across its surface like cosmic claw marks. These delicate arcs stretch for hundreds of miles, vanishing abruptly at the edges of Tethys terrain as if painted by an unseen hand. They're not random stains, they form precise, almost artistic patterns, defying the moon's otherwise frozen stillness. So where did these crimson scars come from? One leading theory points to cryovolcanoes' ice-spewing vents that might have oozed mineral-rich slush onto the surface. On Earth, iron-rich fluids leave rust-colored stains. Something similar could be happening here, with compounds like methane or ammonia breaking down under radiation to create those haunting hues. But there's a catch. Tethys shows no obvious signs of volcanic activity. No fissures, no geysers, just these ghostly streaks lingering like echoes of a long-dead eruption. Then there's the magnetic angle. Tethys orbits deep within Saturn's radiation belts, a zone where charged particles bombard surfaces relentlessly. Could these high-energy assaults be burning the ice, leaving behind chemically altered, reddish residues? Lab experiments show that irradiating icy mixtures can produce similar discolorations, but nothing explains why the streaks cluster in such distinct, narrow bands. If radiation is the artist, why isn't the entire moon painted red? The most tantalizing clue lies in their placement. These arcs align eerily with gravitational stress points, where Tethys' crust might flex under Saturn's pull. That's led some researchers to propose a subterranean leak, a slow seepage of briny liquids from cracks too tiny to see, staining the surface as they emerge. Think of it like tree roots drawing water upward, only here the roots are fractures in the ice, wicking up alien chemicals from hidden depths. Yet for all our theories, the truth remains just out of reach. Unlike Enceladus geysers or Titan's lakes, Tethys offers no active spectacle, just these silent, rust-colored whispers from a past we're still deciphering. Whatever created them left no obvious fingerprints, turning this quiet moon into a celestial cold case. Until we land a probe on those scarlet streaks, their origin will linger in the realm of pure speculation. A reminder that even the most placid worlds can hide the boldest mysteries. If you thought Saturn's polar hexagon was strange, wait until you hear about the furnace hiding above it. While most planets chill out at their poles, Saturn defies logic with an upper atmosphere hotter than a blast furnace, reaching temperatures over 1,500 degrees Fahrenheit. That's not just warmer than expected, it's 3 times hotter than models predicted, as if someone cranked up an invisible heater right at the planet's crown. So where's all this heat coming from? Saturn's dazzling auroras are prime suspects. On Earth, auroras paint the sky with gentle light shows, but on Saturn, they're cosmic particle storms. Charged electrons raining down from space, colliding with atmospheric gases and dumping insane amounts of energy. But here's the catch, even the most intense auroras shouldn't generate this much heat. Something else is amplifying the effect, turning the polar stratosphere into a pressure cooker. One theory points to giant atmospheric waves, rippling outward from the auroras like shockwaves in a pond. These waves could carry energy far beyond the auroral zone, distributing heat with freakish efficiency. Another idea involves Saturn's own winds swirling at breakneck speeds. They might act like a giant mixer, trapping heat at the poles instead of letting it escape. Yet the real puzzle is the scale. Earth's auroras barely warm our upper atmosphere, but Saturn's turn entire regions into thermal anomalies. Could its lack of a solid surface play a role? Without land to absorb energy, heat might ricochet through the gas layers like a pinball. Or perhaps Saturn's magnetic field, stronger and more chaotic than Earth's, is funneling extra particles into the polar vortex, supercharging the furnace. Whatever the answer, this isn't just a quirk of weather. It's a glaring gap in our understanding of how energy moves through planetary atmospheres. Saturn's poles aren't just defying expectations, they're rewriting the rules, proving that even familiar processes can spiral into the extraordinary under alien skies. Deep within Saturn's churning atmosphere, a tempest unlike anything on Earth rages for months or even years at a time. Scientists call it the Dragon Storm, not just for its ferocity, but for the sinuous, snake-like shape it carves across the planet's cloud tops when viewed from space. This isn't your typical thunderstorm. The bolts unleashed here pack a punch 10,000 times stronger than any lightning we experience on Earth, with each strike illuminating an area larger than continents. What makes this storm system so extraordinary isn't just its power, it's its stubborn persistence. While Earth's thunderstorms fizzle out in hours, Saturn's Dragon Storm lingers, churning in the same mid-latitude bands for seasons on end. This peculiar clustering hints at something deeper at work. Unlike Jupiter, where storms spiral chaotically, Saturn's Dragon seems magnetically anchored, as if some invisible force beneath the clouds keeps it tethered in place. The secret may lie in Saturn's internal furnace. Most planets cool as they age, but Saturn emits nearly twice as much heat as it receives from the Sun. That excess energy has to go somewhere, and many researchers believe it fuels these apocalyptic storms. Imagine a pot of water boiling violently on a stove. The heat forces bubbles to rise in predictable patterns. On Saturn, rising columns of warm gas might punch through the upper atmosphere, creating the perfect conditions for sustained, hypercharged lightning. Yet there's a twist. These storms aren't constant. They erupt in decades-long cycles, vanishing for years before flaring back to life with renewed fury. Some scientists suspect seasonal shifts in sunlight could trigger them, while others argue for tidal stresses from Saturn's moons stirring the atmospheric pot. One thing's certain, every dragon storm leaves behind chemical scars, molecules like ammonia and phosphine reshuffled by the violence, creating permanent fingerprints in the clouds. These aren't just light shows, they're planetary-scale laboratories rewriting the chemistry of Saturn's skies one cataclysmic bolt at a time. And until we send a probe deep enough to witness the chaos firsthand, this dragon will keep breathing fire from the shadows. Saturn doesn't stand upright like a spinning top, it lounges at a dramatic 27-degree angle as if tipped by some cosmic hand. This tilt isn't just for show, it's a clue to the planet's violent past. While Earth's gentle lean gives us seasons, Saturn's extreme slant hints at something far more chaotic, possibly a colossal collision billions of years ago, back when the solar system was a demolition derby of rogue planets and asteroids. One leading theory suggests a planet-sized object smashed into Saturn, knocking it off kilter like a billiard ball struck off-center. But there's another twist. Neptune might have played a role without ever touching it. Over eons, gravitational interactions between the two giants could have locked Saturn into this tilted state, a slow-motion tug of war written in the language of orbital mechanics. Here's where it gets stranger. Saturn's tilt shouldn't be stable. Without its rings and moons, the planet's axis might wobble chaotically over time, like a spinning top losing balance. Yet somehow, this system stays locked in place. The rings, despite being relatively young, may act as a gyroscope, their sheer mass helping to steady the planet's orientation. Meanwhile, Titan's hefty gravity could be pulling like an anchor, subtly correcting any drift, but not everyone agrees. Some models suggest the rings and moons arrived after the tilt, meaning they're passengers, not stabilizers. If true, the real mystery isn't how Saturn stays tilted, it's why the tilt hasn't changed since the dawn of the solar system. Could hidden forces deep within the planet's core be resisting further shifts? Or is there an unseen dance with other gas giants still influencing its posture? Every orbit Saturn completes is a reminder of this unsolved puzzle. Whether shattered by impact, nudged by Neptune, or steadied by its own celestial entourage, one thing's clear: this world wears its tilt like a badge of cosmic history, one we're still learning to decode. While Jupiter boasts its famous Great Red Spot, a storm raging for centuries, Saturn plays a different game, unleashing tempests of unimaginable scale only to vanish without a trace for decades. Meet the Great White Spot, a monstrous storm so vast it could swallow Earth whole, appearing like clockwork every few decades before disappearing into the planet's golden haze. Unlike Jupiter's persistent vortex, Saturn's megastorms are fleeting spectacles, erupting with fury before fading into obscurity as if nothing happened. The pattern is eerie in its predictability. Roughly every 20 to 30 Earth years, Saturn's atmosphere convulses, birthing a brilliant white tempest that wraps around the planet like a jagged scar. The last one lit up in 2010, a sprawling electrical storm 10 times larger than any hurricane we've seen, flashing lightning so intense it briefly outshone the rings. Then, just as suddenly as it arrived, it dissolved, leaving only faint chemical traces as a ghostly reminder. Why this cycle? The secret might lie beneath Saturn's clouds. On Jupiter, storms dive deep, drawing energy from the planet's scorching interior. Saturn's storms, though, seem to tap into something different: layers of water vapor trapped beneath hydrogen and helium, like steam building under a cosmic lid. When the pressure becomes too much, the lid blows off, unleashing chaos until the energy dissipates. It's a celestial pressure cooker with a release valve set to occasional apocalypse. There's another twist. Sunlight might be the trigger. Saturn's tilt and long seasons mean each hemisphere basks in decades of summer darkness before flipping to sunlight. Some researchers think this solar switch flips the storm cycle, heating the atmosphere just enough to destabilize those hidden vapor layers. Jupiter, meanwhile, orbits closer to the Sun, soaking up steady warmth, perhaps why its storms never take a break. These disappearing acts make Saturn's storms uniquely mysterious. Will the next great white spot arrive right on schedule, or will it defy expectations? One thing's certain: when it does erupt, it won't just be a storm. It'll be a front-row seat to one of the solar system's most enigmatic weather patterns, a tempest that refuses to follow anyone's rules but its own. Beneath Saturn's swirling clouds lies a mystery that rewrites what we thought we knew about planetary cores. Forget the textbook image of a dense, compact center. Saturn's heart is something far stranger, a fuzzy ball of heavy elements tangled with hydrogen, stretching nearly halfway to the surface. This isn't just a minor oddity, it's a clue that gas giants might form in ways we never imagined. So how do we know Saturn's core is so bizarre? The planet's gravity field holds the key. When Cassini mapped Saturn's subtle gravitational tugs, scientists expected signatures of a sharp, solid core like Jupiter's. Instead, the data revealed a gradual transition, as if heavy metals and rock slowly dissolve into the surrounding hydrogen ocean. Think of it like stirring honey into tea, no clear boundary, just a gradual shift from one to the other. This fuzziness upends classic planet formation theories. Jupiter, with its distinct core, fits the old model. A rocky seed grew massive enough to hoard hydrogen gas from the young solar system. But Saturn's diffuse core suggests a messier process. Perhaps violent collisions scrambled its early structure, or migrating moons churned the inner layers over billions of years. Then there's helium rain. As temperatures and pressures rise toward the core, helium droplets might sink, mixing with heavier elements like celestial paint splattering into wet cement. The stakes: if Saturn's core isn't solid, it challenges how we classify gas giants altogether. Jupiter's compact heart generates a fierce magnetic field, while Saturn's fuzzy one produces a strangely symmetrical field. No tilt, no wobble, as if the entire dynamo is smeared across its interior. Even more intriguing, exoplanet hunters now wonder if fuzzy cores are the rule, not the exception. Every wobble in Saturn's orbit, every ripple in its rings, whispers secrets about that blurred, half-formed core. It's a reminder that even the mightiest planets might be far less tidy beneath the surface, and that the universe loves to defy our simplest assumptions. Saturn's rings might look eternal, but they're cosmic newcomers barely 100 million years old, a fraction of the planet's 4 billion-year history. So where did this stunning ring system come from? One daring theory suggests a long-lost moon torn apart in a violent cosmic cataclysm could hold the answer. Scientists call this phantom moon Chrysalis a hypothetical world whose destruction might explain not just the ring's youth, but Saturn's dramatic tilt as well. Picture Chrysalis as a frozen sibling of Titan, orbiting Saturn peacefully for eons until gravitational chaos threw its path off course. As it spiraled too close, Saturn's immense tidal forces stretched and shredded it, like a marble pulled apart by invisible strings. The debris didn't just vanish, it scattered into orbit, forming the seeds of today's rings. But here's the critical twist: Chrysalis' death throes could have also nudged Saturn off kilter. Just as a falling weight shifts a spinning top, the moon's final gravitational tug might have tilted the entire planet, locking it into that 27-degree slant we see today. The math adds weight to the story. Simulations show a moon roughly the size of Iapetus, big enough to leave a mark, but not so massive it destabilized Saturn's other moons, could explain both the planet's angle and the ring's surprising freshness. And there's physical evidence too. Saturn's rings are almost pure ice, remarkably free of the rocky dust that would accumulate over billions of years. A shattered moon's icy mantle, stripped away before its rocky core plunged into the planet, fits that profile perfectly. Yet mysteries linger. Why didn't Chrysalis remains form new moons, as often happens with disrupted satellites? Some researchers speculate Saturn's gravity was too strong, grinding the fragments too finely for reassembly. Others wonder if the planet's unique magnetic field played a role, scattering the debris into delicate rings instead of clumping them. What's certain is this: if Chrysalis existed, its sacrifice gave Saturn two of its most iconic features, a crown of glittering rings and a regal tilt that defies convention. It's a reminder that even in the serene beauty of the cosmos, destruction and creation are often two sides of the same celestial coin. Saturn isn't just a visual marvel, it's a cosmic radio station broadcasting eerie pulses of energy into space. Known as Saturn kilometric radiation, these rhythmic bursts of radio waves should sync perfectly with the planet's rotation. But here's the catch: they don't. Instead, they pulse like a misaligned metronome, flickering on and off with a timing that defies everything we know about how gas giants behave. What makes these radio pulses so baffling? On most planets, charged particles spiraling along magnetic field lines generate radiation that matches the spin rate, like a lighthouse beacon tied to the planet's rotation. But Saturn's pulses lag behind, drifting out of sync like a clock losing time. Some researchers think this could point to hidden currents deep within the planet, where layers of metallic hydrogen churn unevenly, distorting the magnetic field from the inside out. There's another layer to the mystery. Saturn's radio pulses aren't just irregular, they're seasonal, shifting their rhythm over decades as the planet orbits the Sun. During Cassini's mission, the pulses slowed dramatically, as if something in Saturn's interior was subtly recalibrating. Could shifting solar wind pressure be tugging at the magnetic field, throwing off its rhythm? Or does Saturn's tilted magnetic axis, oddly aligned with its rotation axis, allow sunlight to stir up unpredictable currents in the upper atmosphere? Then there's the wild card, moon interference. Enceladus geysers spew electrically conductive water vapor into Saturn's magnetic domain, potentially disrupting the flow of charged particles that generate these radio waves. It's like dropping a wrench into a finely tuned engine. Suddenly, the timing sputters. Whatever the cause, this radio anomaly forces us to rethink how planetary magnetic fields operate. Saturn isn't just a silent giant, it's a celestial DJ, mixing signals we're only beginning to decode. Every pulse is a clue, hinting at forces deeper and stranger than we ever imagined. Saturn's rings aren't just static bands of ice, they're cosmic history books, etched with ghostly spirals that whisper of ancient violence. These delicate ripples, stretching thousands of kilometers across the rings, aren't random flaws, they're scars from comets that smashed into the rings centuries ago, leaving behind disturbances that still linger like echoes in slow motion. Here's what's fascinating: these spiral patterns shouldn't still be visible. On Earth, waves from a thrown rock fade in seconds, yet Saturn's rings preserve these ripples for hundreds of years, bending but never breaking. The secret lies in the way ring particles interact. Each tiny ice fragment gently nudges its neighbors, passing the ripple forward like a crowd doing the wave in a stadium. Because there's no friction to dampen the motion in space, the disturbance just keeps propagating, preserved in near perpetuity. But there's a deeper puzzle. These ripples aren't just museum pieces, they're actively reshaping the rings. As the spirals unwind over time, they subtly redistribute material, clumping some areas while thinning others. Some researchers compare them to sonic booms frozen in ice, where the initial impact's energy fans out in precise mathematical curves. By studying their spacing and decay, scientists can even calculate roughly when the collisions happened, like carbon dating but for cosmic crashes. What's truly remarkable is how much these ripples reveal about forces we can't see. The way they twist and spread hints at hidden densities in the rings, or even the ghostly tug of Saturn's gravity resonating through the debris. It's as if each ripple is a fingerprint left not just by the comet that made it, but by the invisible hand of physics itself. So the next time you see Saturn's rings, remember, their smooth appearance is an illusion. Beneath that pristine surface, ancient tremors still ripple outward, silent testimonies to a past that refuses to fade. Saturn's atmosphere holds a chemical mystery that's as subtle as it is significant: the puzzling absence of methane. Compared to Jupiter, where methane swirls abundantly in its stormy skies, Saturn's methane levels are shockingly low. Scientists expected similar concentrations, given both planets' shared status as hydrogen-rich gas giants. Yet something or some process is stealthily removing methane from Saturn's air, leaving researchers scrambling for answers. One possibility is simple but profound: the methane might be sinking. On Jupiter, powerful updrafts keep gases churning, preventing heavier molecules from vanishing into the depths. Saturn's atmosphere, though, could be acting like a slow-motion elevator, allowing methane to gradually drift downward where crushing pressures and temperatures break it apart. Imagine pouring glitter into a glass of water. Some floats, but most eventually sinks to the bottom, invisible. Then there's the seasonal twist. Saturn's extreme tilt subjects it to decades-long seasons, each dramatically altering atmospheric circulation. During certain times, cold polar vortices might act like traps, condensing methane into icy crystals that rain out of the sky. Alternatively, chemical reactions we've yet to discover could be transforming methane into other compounds like benzene or acetylene, hiding its presence in plain sight. The wildest theory, methane might be seeping into Saturn's core. Lab experiments show that under extreme pressure, hydrogen can form exotic compounds with other elements, perhaps even locking methane away in molecular cages deep within the planet. If true, Saturn wouldn't just be losing methane, it'd be hoarding it in a form we've never seen. Whatever the explanation, this missing methane forces us to rethink how gas giants evolve. Jupiter and Saturn may look like siblings, but beneath the surface, their chemistry tells wildly different stories, and Saturn's version is missing a key chapter. Every unaccounted molecule is a clue pointing to processes more complex and more alien than we ever imagined. Titan's hazy orange skies hold a fleeting spectacle, a swirling dark vortex that appears and vanishes like a phantom in the mist. These mysterious patches, glimpsed by Cassini near the Moon's poles, aren't just shadows. They're dynamic disturbances churning through Titan's thick atmosphere before dissolving without a trace. Some scientists believe they're methane storms raging briefly in the frigid air. Others argue they could be something far stranger, upwellings of dark organic compounds bubbling to the surface like ink in water. What makes these vortices so puzzling is their unpredictability. Unlike Saturn's persistent polar hexagon, Titan's dark swirls are transient, lasting weeks or months before fading back into the haze. Their murky coloration suggests they're packed with complex hydrocarbons, perhaps the same molecules that rain down to form Titan's dunes and lakes. If they're storms, they'd be unlike any weather we know, fueled not by water vapor but by methane condensing in the Moon's -180°C chill. Yet there's another possibility. These vortices might be Titan's version of volcanic plumes, not of lava, but of slushy organic sludge. Deep beneath the surface, liquids rich in benzene or ethylene could be forcing their way up, creating temporary stains in the atmosphere as they erupt. It's a haunting parallel to Earth's geysers, only here the water is a toxic cocktail of hydrocarbons and the steam is a brew of exotic gases. The stakes are high. If these patches are storms, they reveal Titan's atmosphere is even more volatile than we thought. If they're upwellings, they might point to hidden reservoirs of organic goo, potential incubators for chemistry we've never witnessed. Every flicker of these dark vortices is a tantalizing hint, a whisper of processes that could reshape our understanding of how alien worlds evolve. For now, they remain enigmas, swirling at the edge of our knowledge before vanishing like dreams in Titan's eternal twilight. Imagine an invisible force field so vast it could swallow the Sun, and all its planets with room to spare. That's Saturn's magnetosphere, a colossal bubble of magnetic energy stretching over 1,000,000 miles into space, far enough to engulf Titan, Enceladus, and even the planet's iconic rings. Yet what makes this magnetic giant truly baffling isn't just its size, it's the precision of its symmetry, a perfect balance that defies the cosmic chaos around it. Jupiter's magnetosphere is a lopsided wrecking ball, warped by the planet's rapid spin and tilted magnetic axis. Saturn's, though, is almost unnervingly smooth, a near-perfect sphere of influence as if carved by celestial tools. This symmetry puzzles scientists since most planetary magnetic fields bulge and twist under pressure from solar winds. One theory points to Saturn's unique rotation. Its magnetic field aligns almost perfectly with its axis, creating a stable, streamlined barrier against the solar storm. Another possibility lies deeper in the planet's fuzzy core, where swirling layers of metallic hydrogen might generate a more orderly magnetic footprint than Jupiter's compact heart. But symmetry isn't the only enigma. Titan, Saturn's largest moon, orbits snugly inside this magnetic embrace, its atmosphere bombarded by charged particles that should, over time, strip it bare. Yet Titan persists, its thick haze and methane seas intact. How some researchers suspect the moon's own ionosphere, a layer of electrically charged gases, acts like a magnetic shield, redirecting Saturn's energetic onslaught like a cosmic umbrella. Others think Titan might even leave subtle fingerprints on the magnetosphere itself, its organic, rich exosphere seeding Saturn's magnetic domain with heavy molecules that alter its behavior. Then there's the solar wind's role, a relentless stream of charged particles from the Sun that sculpts Saturn's magnetic bubble into a teardrop shape on its sunward side, while stretching it into a long, comet-like tail behind. During solar storms, this dance turns violent, compressing the magnetosphere until it crackles with auroras brighter than Earth's. Yet through it all, Saturn's field maintains its eerie balance, a silent titan holding its ground against the universe's fury. This magnetic leviathan isn't just a shield, it's a dynamic frontier where moon-borne particles collide with solar winds and invisible forces shape the fate of worlds. And while Jupiter's magnetic chaos steals headlines, Saturn's quiet symmetry whispers a deeper truth. Sometimes the universe's most profound mysteries aren't found in turbulence, but in perfect, unexplainable order. Saturn has dazzled us with its rings, bewildered us with its storms, and whispered secrets we're still struggling to decode. From the razor-sharp hexagon guarding its north pole to the ghostly spokes skating across its rings, this planet refuses to play by the rules. We've watched moons swap orbits like dancers in a cosmic ballet, geysers blast life's ingredients into space, and storms erupt with the precision of a celestial clock, only to vanish without a trace. Yet for every mystery we unravel, a dozen more emerge, each more perplexing than the last. What's truly humbling is how much remains hidden. Saturn's fuzzy core defies our models, its missing methane taunts our chemistry, and its tilted axis hints at ancient violence we can only imagine. Even its radio pulses, blinking like a misaligned beacon, remind us that beneath those golden clouds lies a world stranger than fiction. But here's the thrilling part, we're not done exploring. Missions like Dragonfly, set to soar through Titan's haze in the 2030s, or future probes designed to dive into Enceladus plumes, could rewrite everything we think we know. So stay curious. The universe's greatest stories aren't tucked away in dusty textbooks, they're unfolding right now, in the icy geysers and swirling storms of Saturn. Which mystery captivates you the most? Drop your favorite in the comments, and don't forget to subscribe for more journeys to the edges of understanding. The cosmos is vast, but the adventure is just beginning.